Welcome, everybody. It's March 30th, 2022. This is Introduction to Statistics, the spring 2022 semester at College of the Sequoias. We had just got done talking about the roots of, or the idea of the hypothesis test. We still had a little more I want to talk about. But I wanted to point out, we've got two conclusions when we go through all of our data analysis, which we'll talk about how to do in a second. So this is 9.1, 10.1, 10.1, 10.1 continued, 10.1 continued. So after all of our analysis, we can come to one of two conclusions. About H naught and HA. H naught is our null hypothesis. It's our default one. It's the old news. It's a statement of equality. And HA is the alternate hypothesis. So we've got two conclusions. We've got reject H naught, support HA. And then we've got do not reject H naught, do not support HA. So the do nots go together. Our statement of conclusion, though, is always about H naught or HA. Which is the claim we've been gathering evidence to support or refute. So we've mentioned all that yesterday or Monday. And I did say we're not always right. We can be wrong. So what if we are wrong? In our decision. That's where we're at. So let's look at the two, what they are. So the first one we looked at is reject H naught, support HA. So our decision was reject H naught and support HA. And an error means that the error is rejecting H naught, although it's true. Although, let's just try that again. I did it again. Although it's true. No, that region's bad. This one's okay. This is called a type 1 error. It goes with alpha. And this is like, in terms of the lawsuit stuff, convicting the innocent. Then we could have the other one. Do not reject H naught. Do not support HA. And the error here would be failing to reject H naught when we should have. So we're making our decision, do we keep the old information or reject it? And then we always make our statement about what the new information would be. This error, this is called a type 2 error. And they use beta, which looks like a capital B with a tail. And the equivalent here is like letting the guilty walk free. Okay, any questions so far? Okay, so what do we want to avoid? We want to avoid making type 1 errors. We don't want to convict the innocent. We convict someone of something they go to jail for. It's always on the record, no matter what it is. It stays with them for the rest of their life. They're always considered a felon if it was a felony, and it just ruins their lives. If someone, we'd rather err on the side of the caution and let a guilty person walk free, because we generally will catch them the second time or the next time. This kind of sucks when it ends up being about a murder case. But when it's something less important, like no one dies from it, theft or something like that, it's less important. But we don't want to send someone to jail when it's going to ruin their lives if they didn't do it. And that's where the whole innocent till proven guilty idea comes from. You need the substantial evidence or sufficient evidence to convict somebody. It needs to be there. So that's the idea behind it. It's the same correlation to statistics. We don't want to reject H naught when it's true. We don't want to reject the old information if it's true. So that's why we put this level of confidence, this high percentage on it that we'll see. The alpha that I've been speaking of, the type 1 error alpha, is directly related to the confidence intervals. Okay. For a two-tailed or one of the not equal to situations, the confidence interval is decided as 1 minus alpha times 100%. So when alpha equals 0.05, that's our whole, what's considered unusual, 5%. Our confidence interval ends up being 1 minus 0.05, which is 0.95. Then we multiply it by 100, it's 95%. So when alpha equals 0.05, our normal level of unusualness, 5%, we get a 95% confidence interval. This is when the alternate hypothesis has a does not equal to it. And I'll show you some of the symmetry of that a little bit later. When it happens to be a less than or a greater than situation, this is called a one-tailed test. And here the confidence interval is actually, we got to double it. It's 1 minus 2 alpha times 100%. So if we have alpha equals 0.05, this leads to 1 minus 2 times that. 2 times that, that's like a nickel. 2 times a nickel is 10 cents. This is going to lead to 90% confidence. And I'll show you pictorially why we go with that. Whatever distance we're going, it's going out an alpha in either direction. Well, it's not going out alpha in either direction. It's going out the margin of error in either direction. And the normal setup is when we do confidence intervals is this thing. This is the not equal to situation. We could have it where it's less than. We could have it where it's greater than, so long as it's not equal to. When we restrict it down to one of the, like P equals 0.5, P is greater than 0.5. P being greater than 0.5 is saying, we're all saying it's going one way. So we expect it to be higher. We're only looking for everything that direction. So we only have half that region. It's a little weird, but we'll see how it works out when we're doing it. And keep in mind that alpha is not fixed at 0.05. Okay. Let's see, do I have it coming up where we like to talk about the different levels of alpha? Yes, I do. We'll be going over the levels of significance in a little bit. How we choose that. So alpha here is called the level of significance. You all right, Astro? All right, let's take a look at some hypothesis testing. Actually, while you guys are looking at that, I might be able to that did not work as well as I thought. There we go. Now I could probably shift it. Nope, that's not working. What is going on? I just completely screwed this up. Let's try this again. Bring the camera back up. And oops. Nope, not opening a new window. Stop that. There we go. Let's get MATLAB up and running. Because we're about to start 10.2. Can you guys hear that sound in the background? That's a dog, believe it or not. All right, 10.2. The 5 easy steps of hypothesis testing. Well, 5 steps. I think they're pretty easy. And then we'll start with sample proportions. 10.2 will be sample proportions. 10.3 will be sample means. We're going to try to get them both done today. The reason why I say it's 5 easy steps of hypothesis testing is you will see we have 8 hypothesis tests that we'll do this semester. There are more than that, but this is just an introduction to statistics. We will 8 hypothesis tests we will do. And of the 5 steps, pretty much the only step that changes is step 1. So when you remember the format of how to do the hypothesis test, it's going to transition over to every other hypothesis test you do other than the first one. And when you hear why the first step changes, it's going to make sense. So let's jump into that. What is this first step that I speak of? Why would it matter? The first step is identifying our 2 claims. 2 competing claims. H0 and HA. H0 and HA, like we showed, we did 3 of them on Monday. We showed one that had proportions. We showed one that had means. We showed one that had variance or standard deviation. So all of these have different tests, the way the math is done. In terms of what we're going to do, the computer's going to do all the math for us, so the steps remain the same. We just need to be able to identify which type it is. And then if it's got more than one sample group in it, if we'd like to have 2 samples that we're comparing, it's different. The test is slightly different. And when it's more than 2, it's slightly different. So that's how we end up with 8 different ones. They're all centered around proportion and mean for the most part. So our first test is H0 and HA, and then steps 2 and steps 3 often are interchangeable. I'll just give them to you in an order that I'm used to doing. We're going to find the test statistic and p-value for our problem. And for us, we're going to use StatCrunch to do it. The other one, these 2 are interchangeable, the order you do them in, because it doesn't matter which one you do first. The other one is identify alpha, the level of significance. You want to know how precise you want to be, how much error you're willing to allow. Okay. If it's not listed, set alpha to be 0.05. Now, 0.05 is the one we use most commonly, but there are other options. So like if alpha equals 0.1, we have some evidence against H0. And if alpha equals 0.05, I'm going to put 10 because I think it's easier to see how these numbers are going. We've got fairly strong evidence. Against H naught or versus H naught. And this is going to lead to, in general, a 90% confidence for the not equals. This is 95%. If we drop down to 0.01, we have very, very strong evidence against it. This is like 99%. And if we go to alpha equals 0.001, this is kind of like overwhelming evidence. Or 99.9%. And these are for the two-tailed test scenarios. Give you a second to process that before I give you the last two steps. We haven't done any math yet. Not in any way, shape, or form have we done any math yet. All we need to do is identify what type of, what was the pre-existing case, H naught. What do we think has changed, HA? How sure do we want to be? And then we let the computer do the work to get the results. So I guess there's some thinking to step one. You gotta be able to think about what type of thing it is for step one. Everything else is kind of like just let the computer do it. And picking alpha isn't really that much of a big deal. If you don't know, go with 0.05. If you need this up longer, let me know. Otherwise, I'm going to switch the page. What we have left is steps 4 and step 5. Step 4 is we're going to take our p-value and we're going to compare our p-value, which is given to us by StatCrunch. We're going to compare our p-value against alpha. If the p-value is lower than alpha or less than alpha, we reject H naught and we support HA. So all we got to do is compare two numbers and go, which one's larger? If the p-value is larger than or equal to alpha, we do not reject H naught and we do not support HA. And it is not a common event for it to equal alpha. Like it's usually less than or greater than, but it's not equal to. I have never seen p-value equal to alpha. So while it technically is possible, so is winning the lottery. You know what I mean? It can happen, but it's not common. Now, there's a couple ways to remember this. The clean approach that people like to teach is if the p-val is too low, the null must go. So if the p-val is less than alpha, H naught is the null hypothesis. It's got to go. We reject it. There we go. If the p-val is too low, the null must go. I like to say the same thing, but I tend to go with if the p-val is too low, reject the hoe. It's got that same rhyming cadence to it. And it's really not ho, it's H0 or H naught, but I like it. Okay, so we've decided to either reject H naught or not reject H naught. And so step 5 is our statement of conclusion, and it's always about HA. And you can almost script this. There is sufficient / insufficient evidence to support the claim that, and then rephrase or paraphrase HA. So if the p-value is too low, we support HA. This is the sufficient option. Sufficient or support HA. And the other case would be when it's too high. There's insufficient evidence. To support HA. We never say HA is wrong. And we never say H in our statement, we never say the null is wrong either. What we're really saying, we never say either claim is wrong. Because we rarely know with 100% accuracy what's the case. What we're really saying is we should either stick with the old one which was the do not reject H naught, or let's go with the new one. As there's a lot of evidence against the old one. Okay. Any questions on the 5 steps? We're about to use them, and I think maybe seeing them in the works will be a little clearer. So for the first test that we're doing a one proportion test. Proportion test. I'll often call it the 1P test or one proportion test. And in this scenario, H naught is P equals some value. And HA is P either doesn't equal, is less than, or is greater than that same number. Now, in every one of these hypothesis tests, we want a normal distribution to use these tests. All of them. We want a normal distribution. So we test some stuff for each test. So for a proportion test, we like to check, so to use it, we want to make sure that n times p times 1 minus p is greater than or equal to 10. And we also want n to be less than 5% of the population. I think that green instead. Grab another one. There we go. And also recall for this, these aren't the tests, but these are what we want, or what the values are. Mu of p hat is just p, and sigma of p hat is the square root, of p times 1 minus p over n if we need it. Oftentimes we don't. The computer will do a lot of this work. When we do it in StatCrunch, it's stats, proportion stats, one sample. And you either got to choose with data if you have data values, or with summary if you just have the mean and standard deviation. Usually you have, or usually the summary here is X and N. That's a better way of putting it. So for data, you need all the values. And for the summary case, you need X and N. So those are what we're going to use. I'm about to do our first problem. Are you ready? Tell me, are you ready? Oh, I see something in chat. Oh, you are ready. Okay, excellent. So this is relevant. This is from last fall. These are actual numbers from last fall. It is believed that more than 50% of students, scratch that. Let's go with more than 40%. Let's up it a notch. It is believed that more than 40% of students, or lower it a notch, depending on how you look at it, prefer face-to-face stats classes over online classes. Just holler when you're coming in. I'll turn off the camera. Okay, so in fall of 2021, this was the breakdown for Math 21 without support, and then Math 21 with support. Our face-to-face versus online counts. We had 135 to 550 students that enrolled. And this was 254 to 241. If we add them up, this is 389. And this is, let's see, 197. And we got to add those up. 389 and 791 are, one is, it might be easier to add this way. 135 and 550 is 835. This is 594, and I can add vertically. That's not 8, that's a 6. Astro! And that's 685, not, and that's, so that's 1180. Look at me screwing up the math. Can't count. So if we think more than 40% of students prefer face-to-face, we can check that result here. We got to decide what we're going to consider a success. Hold on one second. We got to figure out what we want to consider a success. If we're going to go with, stick with the 40% for face-to-face, we're going to say picking face-to-face is a success. Which means 389 picked it. And 11,000 or 1,180 students are the sample. This is, administration doesn't think thinks most students want to have face-to-face. The teachers look at how you guys enrolled and said, no, you guys want online. And so we've been fighting every semester over how to set up the classes. So let's take a look at what happens. I'm going to come over here to StatCrunch and I'm going to go, okay, we're going to go stats, proportion stats, one sample. Here, the data would be every person's individual choice by name. We don't have that. We have a summary, so we'll go with summary. And notice it asks for what I had said. It asks for number of successes and number of observations. Just like our confidence interval. Now I'm going to put those in. I'll put 389 as our number of successes. 1,180 students chose Math 21 in fall of 2021. They did not mention a confidence interval. Oh, maybe I should do my steps. What are my steps here? So I see what I got here. It's actually asking me for H0. I got to go with what we said. We said we're talking about P and it's 40%, so 0.4. I didn't actually state the rest of it. Let's say teachers think it's lower than 40%. All right, so HA, our alternate choice, would be P is less than 40%. So I need to put that in here. And notice whatever you put in for P, H0, it automatically changes this down here. Like this was 0.5 and that's 0.5. If I make this 0.95, that says 0.95. So it does that stuff automatically. You have to make sure you put in the right value here and make sure you choose the right sign here. Thank you. I didn't turn off the camera though. But we went for less than, so we're going to go with less than. And we're going to click compute. What we want here is our test statistic, which is Z-stat, it says. Is Z-stat is negative 4.9320954. We're not going to do anything with that. That's more of why do we have that? If we're writing up a paper, we're presenting it in a journal or something like that, presenting it to our peers. We want them to be able to reproduce our tests or our results if they have our data set. So we give them our information, what we got. The other thing we needed here was our p-value. Astro, what are you doing? Astro, go in the other room. Honey, call the dog. Call the dog. Our p-value here is less than 0.0001, which is effectively 1 in 10,000. It's less than 1 in 10,000. We didn't have an alpha here, so I'm going to pick an alpha to be 0.05 since it wasn't given. So I'll use the default. Okay, so we got that. We've got all our stuff from the computer. We decided it was a one proportion test. Kind of like, because they gave us a percentage, they didn't give us any mean or standard deviation. We talked about picking stuff on Monday. How do we pick proportion versus mean and stuff? We look at the words they use. Now we're going to go with make a decision. So we got to compare our p-value versus alpha. P-value is 0.0001. Alpha is 0.05. P-value is less than alpha here. When the p-value is too low, the null must go. We're going to reject H0, which means we're going to support HA. So I'm going to write my final statement. This case, there is, we have enough evidence to support HA. So we're going to say there is sufficient evidence to support the claim that, and what was HA? HA was teachers think that it's lower than 40%. I'll merge some of what came before with that. There's sufficient evidence to support the claim that less than 40% of students prefer face-to-face over online for stats classes. Any questions? So let's walk through it again and just go over what we were doing. What we did was we had to pick H0 and HA. And H0 is the old news or old information. It's a statement of equality. Because in reality, this test wouldn't stop here. We wouldn't just go with stays with less than 40%. They would try to pick a proportion that's right. They would probably say it's around 33%, 0.33. The old news, and then HA is the new claim, and it's an inequality, which means not equal to, less than, or greater than. Steps 2 and 3 are kind of interchangeable. It doesn't matter if you pick H or pick alpha first, or sometimes alpha is just given to you, so it's kind of right away. Find the test statistic. P-value and alpha. And remember, alpha, you'll see level. Sometimes they won't say alpha, they'll say level of significance. So it's important to note that. Step 4 was make a decision by comparing the p-value and alpha. If the p-value is less than alpha, we reject H0, support HA. The p-value is too low, reject the hope. And if it's the other way around, if the p-value is larger, we do not reject H0. And we do not support HA. And I want to show you how this connects to a confidence interval thing. Connecting to a confidence interval. So in the test we just did, we had HA was P is less than 0.40. This is a one-tailed test, which means we want to do 1 minus 2 alpha, which would be 1 minus 0.1 or 0.9, and that leads to 90%. So the way we're going to do this is we're going to put it into the calculator normal. And for that, we need the mean and the standard deviation. And what we're going to do is we're going to set our value equal to 0.9 and let it tell us what X is. Which means if we want mu and alpha, we got to figure them out. So mu was just P, which in this case is 3 or p hat, which is 389 over 1130. And that is 0.32960. And sigma p hat, this was the, I'll write it up here real quick. P times 1 minus P over N. So 0.3296 times 1 minus 0.3296. You don't need to do this. I just want you to see how they connect. And when I do this, I get 0.013685. So I'll move that down out of the way. We're going to go stats, calculator is normal. And squish it down. We're going to click on between. I want to use between. Our mean, I said, was 0.329. Let me just double check those values in the calculator. It's not 1130, it's 1180. I did that earlier too. I got it right here on the screen. 1180. Yeah, 0.3296. I got 0.32966. My bad. And now that I look what I wrote, I actually did write that. So I'll put that in. 0.32966. I'm using a lot of decimal places for some accuracy here. And I multiply that by, then divided by 1180. Then I take the square root and I do get 0.013685. That is not what I wrote. 0.13685. This is where I want to put the 0.9. So I've got my mean, I've got my standard deviation in there. I click compute. And it's not showing what I was thinking it was going to show. What's different here? Oh, the percentage ranges. Sorry. Duh. Brain farting. So we were checking for, notice it says 0.3072 is less than or equal to X, less than or equal to 0.3522. We were checking to see is P equals 0.40 in the range, in the confidence interval. When you do the confidence interval test, you're checking to see if it's in there. 0.40 is not in there. So we reject it. that's the idea we're kind of going with there. How it connects to the confidence interval. Again, you don't need to do the confidence interval. I just wanted to show you how they relate, how this connects to that. It's not in there, so we reject it. Confidence interval supports the same decision. Let's see what else we can talk about before we switch to mean. I got some good problems here. So I'll write down this next problem. Why is this not large? Let me enlarge it. In 1947, 46% of Americans said that they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll of 1,010 adults nationwide, 525 stated that they do not trust the media. At the alpha equals 0.05 level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased? So I'm just going to talk about what I'm reading. And I see that it says 46% of Americans. That sounds like a proportion to me, not an average, like average test score. So I'm thinking the proportion is 46% that we're targeting, which is 0.46. It tells me that 525 did not trust the media out of 1,010 adults. It sounds like the 1,010 is the sample size, and that 525 were in the do not trust, which is the same category as the 46%. 46% did not trust. 525 stated they did not trust. So they're that's the group they're talking about. They give me alpha. They tell me the level of significance is 0.05. I can just throw that down right now. And then they ask, is there evidence to support the claim that the percentage of Americans that do not trust the media has increased? Has increased means goes up. So I'm thinking my HA is going to be P is greater than that 46%, which means H naught is the 46%. And we can see we have that right here. I got it listed down. Oh, where you can find this. You might have to download it. I had to download it because it wasn't wanting to open it when I did it. Let me log into Canvas real quick. Go to Files. And it's right there, Math 21 lecture notes. Will it load up right here? See, it told me an error while processing, but when I downloaded it, I got this. So it downloads fine. Let me switch back to that. It downloads fine, but you might have to download it. It's the Math 21 lecture notes. And I'm just down in section 10.2 on it. So I'm going to use what they said. We're going to go look at StatCrunch. Let me bring up StatCrunch. Where's my StatCrunch? Did it go away? Oh, I have it in tab. Okay. There we go. We'll do it like that. So let's shrink that down for a second. And we won't have it zoomed to window. We will do 100%. Nope, we will make it larger. 200%. That's good for now. So we're going to go in, we're going to go stats, proportion, one sample. Again, we have summary, so we're going to use summary. We're going to say, since the successes was did not trust, we're going to use the 525 that did not trust. And we're going to say N was 1010, like they gave us here. My p-value, or not p-value, my p is 46%, so I got to put that in here. And they went with increased, so we're going to go with increased. We're going to change this to increase. And when we click compute, we get these values. Which are these values right here, hopefully. Should be the same screen. Yeah. Looks a little better over here because this has like no spacing between the groups. But same values. Important thing is Z-stat is 3.813315. And p-value is less than alpha, or p-value is less than 0.0001. And I'll bring up my handy dandy writing document and we'll go from there. Ooh. Does that help? I think that might help. I think I might have just fixed it right there. All right. So step one. Step 2 and step 3 was getting these. Step 3 was given to us. Step 4 is make a decision. So I'm going to compare p-value. My p-value is 0.00, is less than 0.0001, but I can use that. I'll just use that value. We're going to compare that with alpha, or our level of significance. Which is 0.05. The p-value is less than alpha. We are going to, the p-value is too low. The null must go, or reject the hoe. Reject H0, support HA. Step 5 is make a decision. All right, we made the decision. Concluding statement, sorry. So the 0.46 were the people that did not trust the media. And so the alternate is that it's higher than that. The concluding statement is there is sufficient evidence let me write bigger to support the claim that more than 46% of the population. I think they specified like where, like a country or something like that. Don't trust the media. I think that's gone up. These are old numbers. This has definitely gone up. Still got some glare there. All right, any questions? Let's take a look at what happens when we're dealing with a mean. So 10.3 is talking about sample means. Is a one mean test or one sample mean test. And I'll usually write one mu. So here we're talking about mean, and under mean, the way we did that was stats and then t-stats. Since it's one mean, it's going to be one sample. And whether we use data or summary information depends entirely on what they give us. Sometimes we have all the data, sometimes they give it to us summarized. Remember, we want a normal distribution. We need a normal distribution for this to work. So what are the steps for where we got to test for a normal distribution? We either want n to be greater than or equal to 30, and that was like a auto win, all done. Or B, we want no outliers on a box plot. Why is that? There we go. And that's part of B. And then the other part was we want the correlation statistic to be less than the critical value. And we can get that information from a QQ plot. The other category that's kind of considered an auto win is the problem will tell us that the population is normally distributed. Okay. So with that in mind, let's do some examples. I've already got them typed up in this note thing. I'm going to use it. I'll move this over here because might still be copying that stuff down. Maybe I should change my zoom. I'm a little too close. Come down to 10.3 and get to some problems. So we'll go with this problem right here. I'm gonna blow it up so I can make it larger. Assume the resting metabolic rate of healthy males in complete silence is 5,710 kilojoules per day. So I'm going to start writing stuff down on my paper. It says RMR, resting metabolic rate. I'm guessing is how well your body is digesting shit when you're not doing anything. And maybe they measure that by the amount of energy, because a kg is a kilojoule. It's a unit of energy. So maybe it's measuring how much energy you output in normal digestion and stuff when you're just relaxed. And they say, and they mention incomplete silence. So not only are you resting, but it's quiet. And it says males. That might be important. So I'll write healthy males. Might help my statement later on. And they're telling me that the rate is 5,710 kilojoules per day. Now, I know there's no way that every single person is exactly 5,710 kilojoules per day, so I'm guessing that's an average. And it says researchers measured the RMR of 45 healthy males who are listening to calm classical music and found their mean RMR to be 5,708.07. I guess it should be saying with kilojoules per day, with the standard deviation of 992.05. So shrink that back down. Put that zoom back at 160 or 150. I'm going to write that stuff down. I've got n equals 45. They're telling me that the mean RMR for the sample, or X bar, is 5708.07. And they're telling me the sample standard deviation, which is S, is 992.05. And this must be the mean of the population. So that's the population. This is our sample. And so say the normal group is 5,710. And it says at the alpha equals 0.05 level of significance. That seems important. I need that information. Alpha equals 0.05. Is there evidence to conclude that the mean resting metabolic rate of males listening to calm classical music, I think that says calm. Yep. Listening to calm classical music. Ooh, there we go. That might look better. Is different than 5,710 kilojoules per day. So they're comparing it to the 5,710. That's going to be my H naught. My mean is 5,710 kilojoules per day. And they're saying it's different too. They didn't tell me that it's greater than. They didn't tell me that it's less than. So different than, we're going to go with not equal to. And they gave me alpha. So I've got a note of that here. So my step 1 is right here. Maybe I should make alpha step 2 in the future classes. I told you 2 and 3 were interchangeable. Because you don't need 2 to figure out 3. So we need to do our test statistics. So that's going to be in StatCrunch. So we go stats. Here it's T-stats, one sample, and we have summary. They told us n equals 45. That's bigger than 30. So I know it's a normal distribution and I don't need to worry about doing anything else. I can jump straight into the hypothesis test. And they asked for the information that I already wrote down. They want the sample mean, and that was the 5,708.07, which is so not what I wrote. The sample standard deviation was 992.05 kilojoules per day. N was 45. Mu was not 0. Mu is a large number. It was 5,710. And not equal to is my HA, so I'm good to go there. So I'm going to click compute, and it's going to give me some information. It's going to tell me here, notice it says T-stat, not Z-stat. That's from that whole student is the name of the guy. His name was Gosselin. He went on by the name student, but he chose T rather than Z to make it clear it was different. And this says negative 0.013, 050586. Why is that? It's the lighting again. Darn it. So that's the T-stat. And we've got our p-value is 0.9896. And so that's step 3. Step 4 is decide. We're going to compare. I wrote P, that should say p-value. I want to compare my p-value versus alpha. 0.9896 versus 0.05. P-value is bigger here. The p-value is not too low, so we don't reject H naught, and we do not support HA. Okay. We're not done. We need to make a statement. Our statement is about not supporting HA. And HA was that, I'm going to come up here and look at it. This is what I'm looking at. This is the one we're not supporting. No. So I'll make my statement about that. So HA was mu was not equal to 5,710, and we're going with do not support it. So there's now that we don't have enough evidence to support it. You could say there's not enough evidence. I like to go with sufficient and insufficient. That way it just keeps the sentence the same. There's insufficient evidence to support the claim that the RMR of healthy males, I had something else I wrote down, healthy males listening to calm classical music is different than 5,710 kilojoules per day. And I'm probably going to add in, which is the average for males in complete silence. Any questions? We figure out, oh, I see something in chat. Okay, Giselle. Oh, you wrote, yeah, you just wrote that. And this, I'll have this, try to have this video up tonight or tomorrow morning. But you got the gist of it. I'm just going to add a little bit more to it. Oop. Let's look at another example. This is the one I want to look at. Why are you doing that? There we go. So according to the US Mint, quarters weigh 5.67 grams. I'm going to write this down. So weight is 5.67 grams. A researcher is interested in determining whether the state quarters, the quarters that have a different background for the tail or the tail side, have a weight that is different from 5.67. So I guess the 5.67 is non-state quarters. And then state quarters, they want to know, is it different? He randomly selects 18 state quarters, weighs them, and obtains the following data. So I've got 18 numbers. Can I copy and paste these in? I hope I can. I'm gonna copy. What are we trying to conclude here? We are trying to conclude, do state quarters have a weight different? So if the weight is changing or it might be different, the original is mu is 5.67. Different is not less than or greater than, so mu is not 5.67 grams. And so H naught is the one that's the equal to. HA is the alternate one. They give us 0.05 alpha. And I'm just going to hope that I can paste those numbers in here. Control B. That doesn't look like it's going to, but gosh darn it. I guess I can slowly move them all over. That's not too bad. Oop. All right, so we got our 18 state quarters in there. So this is step 1 right here. This was step 3. Step 2 is the computer stuff we're about to do right now. So we have data this time. So we can't use the summary. We've got to use with data. This actually gets a little easier because I don't have to enter anything in. I just got to tell it. Well, I might have had to. The data's in the columns though. I might have had to type the data in. I was thankfully able to copy and paste. We just select the column where the data is, and we tell it what H naught and HA are, and we said 5.67 grams. Computer doesn't care about grams. That's just something we got to keep track of. We wanted not equal to or different, so we're good to go there. We click compute and we get our results. Our results are the test statistic, or T-stat, is 2.7532878, and my p-value is 0.0136. Oh, this alpha is kind of low, or this p-value is kind of low. What alpha did they add? Oh, I already have it. I got my alpha right here. So in this case, we compare our p-value to alpha. Yep, I need to put something right there. I think I know how I'll fix this. And then alpha is 0.05. So 0.013 is less than 0.05. So we have a reject H naught, support HA. HA was that the mean rate is not different. Or not equal to. It is different. Not different. It is different. So there is sufficient evidence to support the claim that the mean weight of state quarters is different than 5.67 grams. Now, I want to point out something. Alpha here matters. If they had wanted to be stricter, if they said 0.01 or a higher level of confidence, our p-value wouldn't have been good enough to reject H naught. So if alpha equaled 0.01, p-value would then be greater than alpha, and we wouldn't have enough evidence. So it does have some bearing. Okay. All right. So a little bit more information I want to give you, and then we'll be done. Statistical significance versus practical significance. When n is really large, standard deviation is really small. Really small. It can get really, really small. So much to the point that in some circumstances, a hypothesis test may show a statistical difference which like where HA, where we're supporting HA, or significance, they say significance also. But the real difference doesn't matter much in real life. Okay, so let's look at an example of that. And I got it in the lecture notes here. In 2003, I'm right here. Statistical versus practical significance. In 2003, the average age of a mother at the time of her first childbirth was 25.2. So that's like maybe 25 years and about 3 months. To determine if the average age is increased, a random sample of 1,200 mothers is taken and is found to have a sample mean of 25.5 with a standard deviation of 4.8. Determine whether the mean age has increased using a significance level of alpha equals 0.05. So we are going to take these values and put them into StatCrunch. Let me make that a little bit bigger. So we're doing stats, T-stats, one sample with summary. And it says the sample mean is 25.5. The standard deviation is 4.8. The sample size is 1,200. And we want to compare that with 25.2. And we're going to say increased. Okay, so 25.2 is here. 25.5, 4.8, and 1,200 was from the words. If we click compute, we get a p-value of 0.0156. A p-value of 0.0156, when we compare it with the level of significance, alpha, it's below. So the p-value is too low. We reject H naught and we support HA. And here we're saying the mean, so HA is the mean value is greater than 25.2. 25.2 though is like 25 years and maybe 2.5 months. 25.5 is like 25 years and like 5 to 6 months. Are we talking about a real big difference in ages of women? Does that seem like, you know, it matters like an extra 3 months? They're still in their prime. It's not like a 25-year-old versus a 40-year-old or a 16-year-old. They're still 25. It's just off by a couple months. That's what they mean by practical significance. While it is significant or statistically higher, we can support the claim that it's higher. Is it really higher enough to worry about? No. So that's what that's what the difference is between statistical significance and practical. Sometimes it says it's significant, but in all reality, no one's going to give a shit about the 3 months. Any questions? I did want to tell you how the final is going to be. We were going to do it on Canvas. Is there anybody still on here? Still in here. Yeah, I still got 2. So the final will be on Canvas, and I'm going to give you 10 problems. 2 of them will have information about confidence intervals. The other 8 problems will have all the stuff for hypothesis tests. You will not have to use StatCrunch. I will give you all the results from StatCrunch. If it's a 1 sample mean, I will tell you that the test statistic, I won't say T-stat, because that kind of, if you study for it, that kind of gives it away. But I'll say the test statistic is this, the p-value is this. I'll give you the word problem. Your goal on the hypothesis test is to tell me H naught and HA, and tell me what kind of decision we're making and give me a sample state or a concluding statement. So I'll do all the computer work for you. It'll be all done. You just have to need to know how this process works and what those decisions are at the end. So hopefully you will find that to be easier. I see a message. Oh, there. Okay. And since the tests are all the same, other than H naught, HA, you really need to be able to identify what kind of tests we're using. And when we get near the end, when we've covered all 8 different types of tests, we'll do a review session on how to pick them apart. Okay. And try to figure out which one's which. And then that's what your test will be. You'll fill in the blank, like tell me the results. The final is like May 10th week, something like that. Let's come over and look at our Canvas. So like you'll have from May 11th to May 15th. The test takes 2 hours. Most people have it done in less than 2 hours. And I'm not going to say most. I think that's a generalization I'm making. Some students have it done less than 2 hours. Some have it done in like 30 minutes. If you're well studied on it, you're really just going through it and answering questions that you understand how they work. If you haven't been staying caught up on your homework, it might take the full 2 hours. It can easily take the full 2 hours if you're not confident in your answers. But if you practice, and I'll give you stuff to look at for a practice, when we get down to the end, it shouldn't take 2 hours. Hopefully it doesn't take 2 hours. All right. let's call that a wrap. Any questions? Nope. All right. I will see you guys later. I am recording if you're good.